Hi, everyone. Thank you for coming. I'm Herman Kwong. I'm a Senior Director of Software Engineering at Salesforce. And with me today is Ping Yan, our lead data scientist and researcher on the security analytics project. And we're here to talk to you about a graph-based method for cross-entity threat detection. I'll be giving you an overview of the security and business context, and then Ping will dive into some of the research results and our approach. Some of you may be familiar with a class of attacks called account takeover. So in account takeover, your attacker already has access to your username, password. They have your credentials. They may have got it through phishing. It may be a weak password. They may have just bought it somewhere, or maybe a keylogger. In any case, they have the keys to your front door. Traditionally, this is more common in financial accounts, right? Like say online banking, when they're logging in to commit fraudulent transactions on your behalf. But more and more often these days, social media and also business applications like Salesforce are also prone to account takeover. And for a site like Salesforce, they will be logging in and attempting to steal valuable information. It could be contact information or it could be financial data from customers. So since they already have keys to your basic defenses, the key to fighting that is detection. You may wonder, if your user already lost their username password through any means, it's their problem. That's just not going to fly, right? If you're running a major web application these days, it's on you, even if the attacker has the legit username password. There are a variety of ways to detect account takeover, and some of these, each of them come with different pros and cons. You can detect things through basic features like where they're coming from, like location or IP. You may have a previous signature on a known attack that you can use, but that requires you to know, to have formal knowledge of an actual attack. You can also use a profile-based approach to establishing what is normal usage for a user, and then trying to catch the activities that are not normal. But that's also prone to a lot of false positives. So generally, the needle in the haystack is not as obvious as on the slide. It's not right there in front of you. The detection is pretty hard. One of the approaches that we at Salesforce are working on is what we call cross links. The basic idea behind this is pretty simple. We're basically looking for unexpected common things across environments or user accounts that should not have common things. So, say if we take a feature or combination of feature of IP address and location, the same combination of that should not come from many different customer organizations. It should only come from one, right? So there are a variety of features that you can use. You can use the browser fingerprint. You can even use the behavior sequence of your user. Again, the key here is finding features or combination of features that should not be common across several user accounts or environments. So with that, Ping will take over and talk about some of the detailed approaches.
All right, thank you very much, Herman. So we did find ourselves a very interesting problem, but at the same time quite challenging, as you can see, because the goal is to find just one to a few malicious crosslinks, and that is often buried under terabytes of data and millions of legitimate connections. So what brings us to success? Well, a good graph-based data model and graph-based algorithms. And why graph is here to save? Because apparently this graph it naturally models the access behavior from your endpoint and to the entity being accessed. At the same time, it reduces computation complexity dramatically because all the computation is localized. Traditional pairwise relationship management would require measurement would require n-squared complexity. At the same time, we represent our data as a multigraph, And because of the nature of multigraph, the solution is highly extensible. That means given a new feature, it could be IP addresses, it could be a user agent string, it could be a geocoding of that IP. It can all be easily and quickly added to the graph, and doesn't change the representation, doesn't change the algorithm itself. So choosing GraphX is a pretty straightforward decision for us because the rest of our detection models are already running in Spark ecosystem, as most of your models are. So we have our detection models running in Spark Core and Spark Streaming, and in the near future, our detection model will be on MLlib. So GraphX as a parallel distributed graph computing engine, it provides the scalability and performance that requires by Salesforce scale. Because at Salesforce, the data points are in the order of tens of millions. And apparently, GraphX provides very easy to use API to instantly use all the advanced graph algorithms. So since this is a research track, a quick scan to the literature, but this is really not a literature review at all. Graph analysis is familiar to everyone in social network contexts. A few examples: proximity-based, PageRank, personal PageRank, semi-rank, or just a few examples there. And in the domain of security detection, actually people have looked into using bridge node for anomaly. And such a bridge node has been discovered in publication network, being authors across multiple research community, or the cross-sector traders. Those are coming from different financial trading networks, or cross-border products in the customer product diagram, or in network intrusion detection, we're seeing people relying on finding cut workplaces to find nodes accessing multiple communities that they do not belong to. So in our use case, we represent our data, primarily application access data, as a bipartite graph. And for those who do not know, a bipartite graph is a graph where you have two sets of, you can divide your vertices into disjoint sets. And the connections can only happen between nodes from one set to the other set, but never in between. So in this two-node illustration, we're seeing a endpoint coming from the single IP, and we call this a feature. So basically, a feature is supposed to uniquely identify an endpoint. And seeing this, accessing a business entity, here's Salesforce. At the same time, we can encode co-access patterns as parallel edges on the multigraph. That is, for example, two business entities, Heroku and Salesforce here, are seeing endpoints coming using the same feature or same signature and connecting both of them. And here we're using an IP and a user agent string as an example. So given this representation, our goal is to detect changes on such a graph. And these changes, if they are cross-entity and expected connections, those are particularly of interest for security reasons. For example, as Herman pointed out in the account takeover scenario, a lot of times it is a single attacker or a single attacker group that employs those compromised accounts to log in from those accounts using the same attacker machine with the same set of signatures, going after multiple user environments and business environments. And it is those connections we're interested in detecting. So we'll talk about two algorithms. One is a naive detector, very simple, and one is a community-based algorithm for such a detection job. Very quickly, a few notations. We have a reference graph that is training data where we encode all the trusted connections. So the connections we know we can trust. And there's the detection graph, basically the training data, where encodes all the untrusted connections, where we need to send to our algorithm to screen for security threats. And anomaly graph and connectivity graph are two derived graph based on reference and detection graph, and I'll talk about them in a little bit. So the algorithm itself simply just calculates the difference between a degree information. And to illustrate, we'll just use this 2 4 nodes diagram. On the left-hand side, we're seeing the reference graph having just a couple of nodes connecting a few business environments, the blue nodes being the features we're trying to identify, and the green nodes are the environments we're trying to protect. And in the detection graph, we're seeing 2 new edges compared to the reference graph. And those 2 new edges are of interest. And the changes are captured by the degree information in this combined graph. And this combined graph between the reference and the detection graph. And as we assign degree information to them, we call it the anomaly graph. So for example, for V1, what we're seeing is like the degree information captured from the reference graph is 1, and the degree information captured from the merge of both graphs is 3. And the change between the 1 and 3 is of interest, is our anomaly score to some extent. So this algorithm continues to run, and if nothing turns out to be positive, the RG-DG merge will replace the previous RG and start the next iteration. Well, I bet a lot of you wants to recode, and that's made it a little bit readable. So the algorithm is very simple, just in a couple of lines of Scala codes. Basically, we initiate a degree info graph where we have 2 degree fields initiated as 0 and 0. And this degree graph, after join with the reference graph of degree information, and this is to use GraphX API after join vertices. So this is how we get the first degree information. And now just join it again. This time join the RG-DG merge. So we get the second degree information. And again, the change of the degree would just be simply a abstraction between those 2 fields. So this is a quick visualization about the bipartite graph, basically a endpoint feature connecting to different business environments. And as we can see, it is a highly sparse graph, and the structure are pretty minimal. And a lot of time it is a one-to-many structure, because that shows a business environment being accessed by multiple unique endpoint features or endpoint fingerprints. And we'll show such a sparse graph structure, basically with very fragmented structure, gives us quite a little information. And how can we look beyond the structure and derive the second version of the algorithm? Because apparently, the first version of the algorithm is very simple and allows us to quickly discover unexpected connections. But at the same time, a lot of times, those unexpected connections are entirely for legitimate reasons. For one example, a AWS server can be employed by multiple businesses. So on our platform, it is no surprise to see connections goes to multiple accounts from the same IP addresses, right? That is why we derive the higher order of connectivity behavior. So basically, this is a business entity connecting to other business entities and to form business communities. The higher order of connectivity are derived by the bipartite graph, basically meaning 2 nodes, 2 business entities. If they are accessed by one single common node from the bipartite graph, then we build a connection between them. So this way, we obtain a second-order connectivity structure on the business entities only. And this way, we can see this hidden kind of structure between all those business accounts. And this way, we use such a higher-order connectivity to identify such an anomaly, so we can reduce noises down to an acceptable level. And apparently, this connectivity graph structure is much more stable than the previous one. So as we see this connectivity graph, we simply just employ the connected components algorithm implemented in GraphX to identify business clusters to approximate the communities among all those business accounts. And now the anomaly detection algorithm becomes to finding detections to highly disjoint business communities instead of single business accounts. And the algorithm itself doesn't change that much. So a quickly walk down step by step would be we derive this higher order connectivity relation given the endpoint to business entity access connection. And we built the anomaly graph as we see in the naive detector. And as we discover communities or connected components on this connectivity graph, we simply collapse all the cluster of nodes into one and run this naive algorithm again to derive the updated node degree. So we get the second order anomaly given this algorithm. Experiments just to see the feasibility of the solution itself on a certain scale. So we take a small sample out of Salesforce traffic, and this reference graph contains about 2 million nodes and a similar amount of edges. About 5,000 business accounts are involved in this experiment, and we identified about 1,000 connected components. So with the naive algorithm, we were able to identify about 700 first-order anomalies given a certain threshold. And we were able to identify about 200 second-order anomalies using the making use of the connectivity graph. So we're seeing a pretty significant reduction in noises here. And all of this just took about 5 minutes on Mac-Air with a very standard configuration. So this has a lot of promises in terms of both scalability, performance, and efficacy in terms of accuracy in identifying anomalies. So this visualization is built on top of the connected graph. This is the connections between all those business accounts, business environments. So what we're seeing is there's a big thick circle outside of this ball. And these are the smaller or highly disconnected nodes. And we're seeing some pretty interesting shape there, but mostly less connected. But in the very center of this, whatever bowl-shaped thing, there is a big cluster of different business accounts. And there are few business accounts connecting to many other entities. So those are typically the services or businesses providing support or services to other organizations. So no wonder there are a lot more interactions between them. So just very quickly, this is a stack that allows us to run such an interactive analysis with both GraphX and visualization. Simply, the data runs from HDFS to Spark, and data will be loaded into a graph structure, so GraphX can run on them. And visualization is supported by this awesome tool called visualization, called Lightning Wiz. So thanks to the guys behind this great tool. And the code are running on Jupyter Notebook. Then the Jupyter Notebook connects to GraphX and Spark Engine via Spark kernel, and Spark kernel is now known as the Apache Torrey project. So now, down the road, we have a number of very interesting, exciting opportunities to allow us to do a lot more with Graph and with security intelligence management. So GraphX itself is a computing engine, and to allow us to have real-time or near real-time updatable and curable databases, we plan to look into graph databases. Also introduce probabilistic edges so we can encode much more complex semantics among all our vertices and entities. So given a probabilistic graph, we need to look into a clustering algorithm to allow us to do a high fidelity community detection to have the anomaly detection algorithm to run. With that, that is the end of the presentation. So we still have plenty of time for Q&A. Please.
Questions? Right there? Okay.
Thank you for the talk, and the graph looks really amazing. I'm just curious. You mentioned about this talk is about threat detection. So based on that graph, how can you tell? Could you show some example like this is a legitimate, business usage, and maybe some nodes or like communities like threat? I couldn't tell from the graph. So.
Yeah, definitely. That is a very good question. Visualization part, actually, there is a lot of room we can improve. So right now, we're able to encode all the connections and have no differentiation between legitimate versus malicious connection. So this kind of just gives us a view of the structure of the data and gives us heuristics so we can apply in reducing or in improving the detection. And the algorithm itself and the results coming out of the algorithm is not shown in this visualization. And that is sort of due to the limitation of the tool itself.
What we are showing in the big graph, you can say, is a more realistic. So we actually ran through actual data to create the reference graph. And then that could be used as we see new traffic coming in to decide whether the new traffic fits with what we expect in the reference graph, or is it anomalous?
Question?
How long does it take for your algorithm to train on the reference graph? Because these graphs are very dynamic. So if your training takes longer than the update, that would be a problem.
So in our experiment, it was a 2 million vertices graph, and training pretty much just about loading that many of nodes. And it takes less than 2 minutes to have the graph built. And as you can see, it was a simple degree calculation on the graph. So that didn't take much time either. The graph itself is pretty big. However, the change between different snapshots of graph are relatively sparse and small. So as we continue to train different versions of such a graph, it gets stable, more and more stable. So we do not expect a big performance downgrade if the.
So your training data is like a number of vertices with degrees on it, like attributes with degrees, and then you compare that against new graph with attributes and other degrees. Is that right?
That is exactly right, yes.
And how did you compare the distance between the, because that almost becomes like a series, like a time, almost like attribute and value, attribute and value. And then you have another set of attributes and value. So you have a distance calculation between the two, right?
That is true. That is why I mentioned the next version is going to be looking into probabilistic edges. So the probabilistic edges will allow us to encode such a distance based on multi-feature and multi-relationship between those two nodes, between those pair of nodes.
Are you willing to reveal what algorithm you use to calculate the distance between the training graph and the test graph?
Right.
And the
For version 1, we're not focused on the distance, just whether they're connected or not.
It is
So
a
whether
binary.
the different environments share the same features, and a lot of times we don't expect them to share the same features.
So for sake of discussion, you've got V1, V2, V3, V5 with degree 1, 5, 3, 2, 1, and you've got another V1 through V something, and you've got a different set of degrees. How did you compare the two?
I think when you say V1, you mean vertex 1?
Vertex, yeah.
When I say version 1, we're not focused on the distance between the nodes, but just the fact that they're connected or not.
Yeah, but you said your input to your algorithm is the vertices and the degrees, right? And then you got array of vertices and array of degrees, and you got, in the test, you got an array of vertices and array of degrees. How did you find the difference between the two?
If I understand you correctly, right now, yes, a degree is just encoding like one single binary connection, right? We got that. Okay. So the distance between those degree information right now is just a abstract, one degree abstracting the other degree. Yeah, it's just a simple arithmetic difference.
More questions?
Do you have any weights or any other data propagating through the bipartite graph edges, like one way or other? Say like whether the importance of the node or any other data propagating like back and forth, and then like you trying to figure out, okay, whether the convergence of the importance is like being measured over there.
That's the opportunity that Ping wants to expand. So right now, for each graph, we have to pick a feature and build that graph for that feature. I think, like you said, the obvious next step is to incorporate multiple features into the same graph and have weights around them for, instead of just whether it's connected or not, it becomes a more probabilistic approach to whether they should be connected or not.
Questions here?
Quick question, whether you have considered doing any sort of a summarization in order to discover normal behavior, like MDL-based compression or sparsification or any other type of summarization?
That's a very good point. Yes, we did some of those summarization statistics in our preliminary analysis, yes.
What techniques are you considering?
Some pretty standard techniques like PageRank or risk propagation. Centrality about nodes or size of nodes. So that would help us to identify, big false positive risks. Because a lot of times we're seeing is, yes, some of the entities, they're showing anomalous behavior, but that anomalous behavior seems to persist. And it is just because of, that is pretty much just normal per entity type of thing. So how to capture that normal behavior and avoid identifying them as anomalies in the next iteration or the future iteration, that is going to be a very interesting aspect to this algorithm. Yeah.
Thanks.
Thank you.
More questions? We have a few more minutes. Anyone? All right, let's give them a hand.
Thank you.